All right, welcome to class for Friday, April 10th, 2020. Today we're talking about supernova, which is actually what we're talking about today. Turns out a supernova is a fantastic example of what happens when you have almost perfectly elastic collisions. So it's fun. It's fun stuff. This actually is a picture of supernova 1987A, which was a supernova that went off in 1987. Scientists love this because it turns out it's the closest supernova to go off that we've observed to go off in the past 400 years. So for some reason, there were 3 supernova very close to us that happened in the late 16th and early 17th centuries, and nothing since, except for this guy. But this wasn't even in our galaxy. This was in a neighboring galaxy. So, you know, we're all crossing our fingers that some star blows up nearby us so that way we can get a good view of it. Okay, reminders for today. So the Wiley Plus Chapter 9 homework and adaptive practice are due, and I'm putting that in quotes, today. Remember, I'll actually bump the due date back a week to tomorrow, probably. There may be a brief period where it says you can't submit the homework anymore. I want the due date to expire because it doesn't actually show grades until the due date passes. But then once it passes, I'll bump it back. But just as a real warning there, I want this to be flexible for you guys, but at the same time, if you let this get really behind, it will just overwhelm you. The more you get behind on these things, the harder it will be to catch up. So I'm doing this sort of rolling back of the due dates because I recognize that a number of you have unstable circumstances that make it hard to work around due dates. But please don't leave this all to the last week of the semester. It will not work. Okay, the other thing to remember is that there's a perusal reading for Wednesday. We'll do an intro to rotation. And there's video experiments 4, which was posted on Wednesday, and 5, which was posted yesterday. 5 really goes along with what we're talking about today. They're both available on Blackboard. Have fun. The next video experiment probably won't go up until Wednesday or maybe Friday of next week. So you've got a little bit of time to take on 4 and 5. They're fun. It's a series of 4 is a series of inelastic collisions, and 5 is a series of elastic collisions. And then if you're having trouble with the video experiments or any other part of the class, I really strongly recommend coming to office hours. Come to office hours, either stick around right after class and ask questions, or Sean is doing office hours on Mondays and Thursdays from 11 a.m. to 1 p.m. So take advantage of that, or, you know, stick around after class. Those are some good resources. I wish I could tell you to go to 110 in the Physical Sciences building and talk to tutors, but unfortunately, we can't get into the Physical Sciences building even if we wanted to. So we'll just do our best with that. Okay, one other thing that I'll point out, and I pointed this out before I turned on the recording, but in the chat, I've posted links to the slides for today and to a spreadsheet that we're going to be using. So hopefully those will help you if you're looking to follow along. Okay, any questions about course administrative blah de blah? All right, we will move forward. Okay, here's your clicker question for the day. All right. So you've got two carts on a track. They collide in such a way that they don't stick together after the collision. Which statement is true? So both momentum and kinetic energy must be conserved. Both momentum and kinetic energy may be conserved. Momentum must be conserved and kinetic energy may be. Momentum must be conserved and kinetic energy must not be. I suppose there should be a B at the end of that one. Or E, which I don't have an option for. Kinetic energy must be conserved and momentum may be. Okay, I'll give you another 15 seconds. Going once. Going twice. All right. Okay, anybody want to vote E? I didn't actually have E as an option on the poll. All right, nobody likes E. Okay, so the most popular answer here was C. So somebody defend C for me.
Momentum is always conserved in any interaction, and then kinetic energy maybe because it can be dissipated with things like noise or heat.
Okay, so why not must be conserved?
Because it can be like it cannot be conserved with things like heat where it's no longer in the two objects, but it's still there.
Okay, so why not kinetic energy must not be conserved?
Because it can be conserved theoretically.
Okay, what do we think? Anybody else like that? It can be conserved?
I like his explanation. And on the why it's must not is wrong, is it can be perfectly elastic.
Okay. So I like this question because it requires you to debate a little bit. So when two carts collide on a track, right? Is there any way they can collide without losing any energy for real carts?
No.
Yeah, so it kind of this question is designed to help you debate that a little bit. Now, you are right that we do talk about perfectly elastic collisions, but it turns out that real collisions, macroscopic collisions, I shouldn't say real, macroscopic collisions. By macroscopic, I mean everyday objects, right? Things that are not atoms or electrons or things like that. When everyday objects run into each other, there's always some energy loss. In fact, you'll see when you look at the video experiment number 5 that looks at some perfectly elastic collisions, or as close as we can make them. These collisions are set up using magnets. So there's same polarity magnets on either side, which means the carts don't ever actually have to touch each other, right? which should preserve energy pretty well. But we'll find out that they don't actually perfectly preserve energy. So anyway, this question is one that that is good to have as a clicker question because you can make a good argument for C or D, right? As has been said, momentum always has to be conserved, right? So that eliminates B and E. And kinetic energy doesn't have to be conserved, right? It could be, but there are lots of collisions where two objects bounce off each other and they still don't conserve kinetic energy. Okay, let's do one more. This is going to require you to do a bit of calculation. So you've got two identical cars, right? And they collide in a T-bone collision. So does everyone know what a T-bone collision is?
Yes.
Give me a thumbs up if
When one gets hit from the side.
right. So you have one car going, in this case I'm saying car A was going west and car B was traveling north. The two cars stick together after the crash. And we're going to assume nothing flies off of the cars, right? In real collisions, stuff flies off of cars all the time. Glass, fenders, whatever. But in this case, we're going to say nothing comes off of the cars. They just stick together. They were both traveling with the same speed before the collision. What's the speed of the two cars immediately after the collision? We're going to assume we can ignore all other forces during the collision. So let me relaunch the poll. There we go. Can you guys see it? All right. I'll give you a little bit of time to work on this one.
The right answer for the first one was C then?
The right answer for the first one, I would say, was D, but C is a pretty good answer too. Okay, I'll give you another 20 seconds on this one. And I really need to get an E for this.
I don't think E is an option on the poll.
Yeah, that's what I'm saying. I think I could change that, but I haven't figured out how
Okay.
yet.
One thing I just realized about the poll is it seems like you can select multiple answers. So that's maybe how you got 12 out of 11 responses.
Right. Yeah, it's a nice feature. All right. Last call. Going once, going twice. Sold. All right. So does somebody want to so what I'm going to try to do here, I'm going to try to do this on the document cam, but I want you guys to tell me what to do here on how to figure this thing out. Okay, so walk me through your solution. Feel free to chime in, and I'm going to try to. This is my attempt to have you guys come up and write on the whiteboard, right? So I'm just going to write what you tell me. So unfortunately, that means I have to stop sharing my screen to do that. But if I stop sharing my screen and I come over here to the document camera. All right. So how do I do this? How do I start this problem? How did you start this problem?
Picture.
A picture. We love a picture. Okay. So we had car A going north, right? Or west. B was going north. Okay, so there's A. Here's B. That one's going that way. That one's going this way. And they both have speed V naught, right? Okay. Now what?
Because they're both equal, I figured out that after they hit, they're gonna go off in a 135-degree angle right there.
Okay, so you're saying this is our before, and over here we're gonna put our after picture,
Yeah.
right? And after you've got, I don't know, blob that's B plus A, right? And it's gonna be traveling, you said this way,
Yeah, exactly.
right? And it's gonna have some speed. What do we want to call that speed?
Mark.
A what?
Mark.
Mark? Mark.
Oh, I don't know. I'll just make something up.
Mark's great. We'll call it V Mark. Because, Mark's a nice guy. Okay. What else do we know here? We've written down stuff we know about velocities. What else do we know?
They move together.
They move together, right? They stuck. Okay. So that's important. What else? What do we know about the masses of the cars?
They're equal.
They're equal because they're identical, right? So this guy had mass M, this guy had mass M. So how much mass does this guy have?
2M.
2M. All right. So now what do we do?
I use the Pythagorean theorem.
You use the Pythagorean, to break this guy up. Is that what you're saying?
Yeah.
Okay. So you could guess, right? But basically, this problem would be the same if we rotated it around, right? So you know that you had the same amount of momentum going this way as this way. So that has to be the same here and here, right? So this leg of the triangle, right, has to be the same as this leg of the triangle. Okay. So now what? What's the same before and after?
Momentum.
The momentum. Okay, so let's write it out. What momentum did you have before?
2 V naught M.
Did you? Which direction was this momentum in versus this momentum? So remember, momentum's a vector, right? So when we add it, we have to add it like a vector. So let's write it out in vector form. What this means is we're going to have something like the momentum of cart A plus the momentum of cart B, right? So which direction is the momentum of cart A in?
Before the crash,
Yeah, before.
towards negative I.
Yeah. Okay, you engineers love to use that IJK stuff, right? So we'll do it your way. Negative M V naught I hat, right? Because it's in the X direction or the horizontal direction or whatever you want to call it, right? You could write this as X hat. You could write this as, so I'm going to write this the same thing 3 different ways here. I could also write this as negative M V naught X hat. Or I could write it as negative M V naught comma 0. Those are all the same thing, right? They're just different notation for the same idea, that this momentum is in the X direction. Okay, how about for B? What does B's momentum look like?
Uh, 0 M V naught.
Okay, so if you did it this way, you do 0 M V naught, right? What if you did it with this I hat business?
Isn't it J?
Yep, that's what you engineers like to use, J hat. Or I could write it as M V naught Y hat, right? Doesn't matter which one I use. They're all the same thing. Okay, so this is our initial momentum. What about our final momentum? Well, we already figured out that this triangle here, right? This is a 45-degree angle. Because as we were explaining earlier, right? These two sides of the triangle have to be the same. So that means we're just going to have some PA plus B, right? The new smashed up car, which is going to be, how would I break that up into this kind of vector notation?
The vector P A plus B, that would be the hypotenuse, right? Of the
Yes.
triangle. So we probably have to work with the angle to get the components. Or
Yep. Yep. So if this is a 45-degree angle, which was being argued earlier that it has to be, right? If that's a 45-degree angle, it means these two legs have the same length, right? And if they have the same length, that means that the sides here have to have length of, right? Because we know that our hypotenuse squared has to equal our two sides squared, right? So it's going to be 2 times, we'll call it VS for the sides, right? Which means that V side has to simply be the length of the hypotenuse divided by the square root of 2, right? Do you see how I did that?
Yeah.
Okay. So that means we've got this much velocity in both the X and Y directions, or the negative I and the J direction, right? Or however you want to write it. But I could write that as, so this is going to look like negative 2m, right? Because this thing has twice the mass now, times this Vs in the I hat direction plus 2m Vs in the j hat direction, or negative 2m Vs x hat plus 2m Vs y hat, or negative 2m Vs comma 2m Vs. Right? And all of these are equivalent statements. Conservation of momentum says they have to be. The momentum before has to be the same as the momentum afterwards. Okay, what's cool about this? Oh, I'm getting ahead of myself. Okay, now what do we do? What do I want in the end of this?
The speed.
Right, which we called mark, right? And we know how to relate that to Vs, so that's good. And we want it in terms of what? What did all the answers have in them?
V naught.
V naught, right? And we've got equations here that tell us how to relate Vs to V naught and Vm to Vs. So we just got to pick one of these things and solve them. Now, here's the really cool thing. You'll notice that these equations are all the same. It's the same equation in X as it is in Y. Because we realized that it had to be going off at that, 45-degree angle here in the triangle, and that these two sides had to be equal. We saved ourselves from having to do an X equation and a Y equation. We can just pick one. So which one do you want to do? You want to do X or Y? I or J?
J.
J. We love J. J is wonderful. Okay, so the J equation says that m v naught, ignore that, is going to be equal to 2m vs, right? My masses cancel, and I get that vs is v naught over 2. Now I come over here, because what I really want is what we call mark, right? And I say that's equal to v mark over square root of 2. And if I solve that thing for v mark, I get that it's v naught over the square root of 2. Okay, so the right answer here was D. All right, how do we do it? What was that?
How did you do the last part? Like, why'd you set v naught over 2 equals v mark root 2?
Oh, right here? Because we know, because they equals Vs, and we knew up here that Vs is just v mark over the square root of 2. Another way to write this is that Vs is v mark times either sine or cosine. You could pick whichever one you want, of 45 degrees. Okay, the cosine of 45 degrees is 1 over the square root of 2. Right? Or you could do it by using the Pythagorean theorem. If you realize, so this is your c squared, right? Your hypotenuse squared, and your a and your b are equal. So a squared plus b squared is just 2a squared, right? Or b squared. They're both the same. So we just use this piece. Okay. So the tricky part here, and the reason I asked this question, is because we got to remember that momentum is a vector, right? So we can't just add northward momentum and westward momentum. They're different things. The same way we can't add velocity, right? Or I should say, we can't just add the magnitudes. We have to think about the direction as well. Okay, how we feeling? Nah. All right. Let's talk about supernova because it's fun. Okay, so this is a diagram and it's schematic, right? This isn't actually to scale or anything. But this is a diagram of what the inside of a star looks like right before it goes supernova. Okay, so you guys, let me give you the very quick rundown on how stars work. Stars are fusion bombs, right? Stars are basically the exact same thing as a hydrogen bomb if it were really, really, really big. It's so a star has so much mass that instead of the fusion reaction blowing it apart, gravity holds it together against that explosion of the fusion energy release. So stars like our sun are powered by a constant fusion reaction that's going on in their cores that is turning hydrogen into helium. Okay? When you turn hydrogen into helium, you take 4 hydrogen atoms, you smash them together, you make 1 helium atom, you lose a tiny bit of mass. And that tiny bit of mass gets converted into energy. And probably the most famous physics equation of all time, E equals mc squared, tells you that if you take a little bit of mass and turn it into energy, you get a ton of energy. Okay? So that's what our sun is doing. Our sun, at the center of it, is turning hydrogen into helium. If in the case of our sun, it's going to stop after it runs out of hydrogen. It will burn a little bit of helium, but not much. Okay, but stars that are more massive than our sun, they can continue that process. When they run out of helium in their cores, they can start burning. Or when they run out of hydrogen in their cores, they've turned all the hydrogen into helium, they can start turning helium into carbon. And when they run out of helium, they can start turning carbon into neon. And when they start to run out of carbon, they can run neon into oxygen, to silicon, all the way up to iron. Iron, it turns out, is special. Okay, you can get there are 2 types of atomic bombs. There are fusion bombs and there are fission bombs. The fusion bombs take really heavy elements like uranium or plutonium and break the atoms apart. And by breaking the atoms, you release energy. Okay? Fusion bombs do the opposite. They release energy by putting atoms together. So when you take light atoms and put them together, you release energy. It turns out iron is the tipping point. If you take an iron atom and you fuse it with something, you lose energy. If you take an iron atom and you break it apart, you also lose energy. So stars will just keep burning heavier and heavier elements up the periodic table until they get to iron in their cores. Okay? When they get to iron, they can't do either. And so they just grow a big iron core in the center of the star, which is crazy to think about, right? The center of these stars, you just end up with a huge ball of iron. but that's what happens. Okay, so you build a huge ball of iron. What does that do? Well, it just keeps getting bigger and bigger and bigger. And it turns out that when you hit 1.4 solar masses of iron, okay, so 1.4 times the mass of our sun worth of iron in the core of a star, something amazing happens. And that is that iron collapses. The iron goes through a really, really dramatic nuclear reaction where it smashes all of the electrons into all of the protons. And you end up with a ball of neutrons. This is called a neutron star. Okay. It is a neutron star is the is an object that will have several times the mass of the sun, but will be about the size of Chico. So this thing is incredibly dense, incredibly dense. It's like one giant atomic nucleus. So what happens to the star is you've essentially removed the center of the star. Well, it's like pulling a chair out from under somebody. When you pull the chair out, everything on top of the chair falls. And so the whole star starts falling inwards. Okay, all of those other layers of stuff on top of the star fall inwards. And because you burn to heavier and heavier element, each layer as you go down is heavier than the one above it. So you get an interesting reaction. So that silicon layer, the iron layer has crushed down into something incredibly small and dense. So that silicon layer comes crashing in, hits that incredibly dense object in the middle, and bounces off of it in something close to a perfectly elastic collision. But the problem is, it immediately runs into that oxygen layer that was right on top of it. And the oxygen layer then immediately runs into the neon layer and the carbon layer and the helium layer and the hydrogen layer. And you end up blowing the star apart. Okay, here's the demonstration of how that works. So we'll go ahead and watch this thing. Hopefully the video loads well for you. If it doesn't, feel free to get at it yourself sometime. But this is a cool experiment. It's way more fun to do this in person, okay? Can you guys hear the sound?
I don't.
Can you guys hear the sound? There should have been sound there.
No sound.
Okay, let's try this. Let me try that.
And the golf ball. Now I'm gonna try the golf ball.
How about now?
Check out how high these different balls bounce.
Yeah.
Okay. All right. So we're gonna watch this.
Basketball, the super bouncy ball, and the golf ball. Now I'm gonna try the golf ball on top of the bouncy ball, on top of the basketball. And then I'm gonna explain how it's related to a supernova. Did you see that? Probably not. So here it is again. The golf ball bounced to 28 feet. We dropped it from about 3.5 feet, so it went up 800% of its dropped height. In fact, if you consider that by itself, the golf ball bounces about 70% of its dropped height. It went as high as if it had fallen from 40 feet up. That is awesome. So how can we get the golf ball to bounce up with that much energy? Let's simplify it to these two balls. When you drop them individually, each ball starts out with some potential energy from the height of the drop. As the balls hit the ground, some energy goes into heating up the ground and some goes into heating the ball. Because that energy left the ball system, you can't get back up to the same height. But when you combine them, the tennis ball goes higher than its dropped height. Way higher. Where does it get the extra energy? As the basketball bounces, it compresses, storing elastic potential energy. As it releases, it springboards the tennis ball upward just at the right moment. This is like the double bounce on a trampoline. When you
Oh, dang it. That was me. Sorry. Try that again. think we were right about there.
Tennis ball. But just like the double bounce preparer, the basketball can't go as high. You can see that here.
We gotta go back. Sorry.
Way higher. Where does it get the extra energy? As the basketball bounces, it compresses, storing elastic potential energy. As it releases, it springboards the tennis ball upward just at the right moment. This is like the double bounce on a trampoline, when you jump right before someone else. You prepare the elastic of the trampoline by stretching it and storing energy, which can then bounce the jumper even higher. In the same way, the basketball stores energy in its compression and is able to push the tennis ball. But just like the double bounce preparer, the basketball can't go as high. You can see that here. It bounces even less when 3 balls are dropped together. Also, during that transfer of energy, some momentum transfers from the basketball to the tennis ball. And since the basketball starts with way more momentum because of its larger mass, the tennis ball's velocity increases by a lot, and it flies up, up, and away. Now back to the triple super ball bounce. Now you get the energy from the basketball's bounce being transferred into the bounce of the super bouncy ball, which is then transferred to the golf ball's bounce. You put the same amount of energy or momentum from 2 more massive objects into a smaller object, and it will go much faster. Epic! Just like the explosions of a supernova, which may seem unrelated, but what we just did is analogous to the process that occurs during the explosion of a supernova. Just like our more massive basketball transfers momentum to the smaller balls, energy from the dense core of the supernova is transferred in a shock wave that moves through the star to the less dense layers and accelerates them outward at a super high velocity. More massive or denser layers in the core of the supernova begin to collapse when fusion stops there. The collapse is halted when the neutrons in the core actually touch, sort of. This causes the implosion to rebound and bounce outward. You end up with a dense core left behind and these wild outer shells of star exploding outward. Pretty cool. And of course, if you try this at home, which you should, you have to make sure the balls are perfectly vertically aligned because any off-centeredness gets amplified by the 2 points of contact, which is why we sadly couldn't get the quadruple tower of balls to work. But if you put a little ring of hot glue or something similar on the balls, it helps to balance them. Happy physicsing!
All right. So hopefully you could watch that. So we're actually going to do this. We're actually going to go through and figure and calculate what would happen in this, and we're going to do it with a set of 3 balls. Okay. So the basic idea, and you heard her kind of allude to it, right? Is this has something to do with energy and momentum and blah 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 blah, right? But we're actually gonna solve the thing because we're gonna do the actual math because that's what we do here, right? So basically what you have when you have those 3 balls dropping, right, is you have a set of collisions that happen, right? The first collision is between the first ball and the ground. The second collision is between the first ball and the second ball, the basketball and the bouncy ball. And the third collision is between the bouncy ball and the golf ball. And those 3 collisions, right, are what result in the golf ball getting a ton of momentum, right, or a ton of energy. You could phrase it either way. That's why the golf ball goes up as high as it does, okay? So what this is this is close to a perfectly elastic collision. And what I've done here is I've written out our equations, right? So we can think of it this way. We have 2 objects, right? Mass 1 and mass 2. And beforehand, they have V1 and V2. Okay, what if it was going the other way? What if mass 2 was going to the left instead of to the right before the collision? How would this change my equations? Don't all shout at once. Let me ask the question again. If I wanted to, I have this set up so that beforehand, mass 2 is moving in the same direction as mass 1, just slower, right? What if I wanted to make it so that mass 2 was moving to the left instead of to the right? how would that change things?
Would it just make the difference between the two velocities greater?
It would, right? And mathematically, all I would do is make this negative, right? I just say this is a negative V2 instead of a positive V2. So I can do this for any velocity in either direction, as long as they're in a straight line, right? And that was the thing that the girl in the video was talking about lining the balls up correctly, right? Otherwise they're not in a straight line, and this becomes a two-dimensional problem, and that's way worse. Okay, so what I've done here is I've written my before momentum is just m1 v1 plus m2 v2, okay? And my before kinetic energy is just 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Does that make sense? Where I got this side of the equations? All right, give me a thumbs up if it makes sense.
Can you explain?
Sure. So here's my situation, right? I've got mass 1 with velocity 1 and mass 2 with velocity 2, and they're all moving in a straight line. So the momentum of mass 1, right, is just its mass times its velocity. And the momentum of object 2 is just its mass times its velocity. So there's our momentum, right? This side of this top equation is the momentum, the total momentum of the two balls before the collision, okay? Similarly, before the collision, this side of the bottom equation is just the kinetic energy of the two balls, right? So ball number 1 has kinetic energy 1/2 its mass times its velocity squared. And ball number 2 has kinetic energy 1/2 its mass times its velocity squared.
Okay.
Okay? And then we're just going to do the same thing for the after, right? After the collision, they're going to bounce off each other because we're assuming this is a perfectly elastic collision. It's not, right? It will not be a perfectly elastic collision, but it'll be pretty close. And the perfectly elastic collision will give us sort of the best case scenario for how high that golf ball is going to go, okay? So again, we're just going to write the momentum afterwards is just the mass of ball number 1 times its velocity, where the velocities before the collision I'm writing as V's, and the velocities after the collision I'm writing as U's. So this term is just the momentum of ball number 1 after the collision. This is the momentum of ball number 2 after the collision. Similarly, this term in the kinetic energy equation is the kinetic energy of ball number 1 after the collision. And this term is the kinetic energy of ball number 2 after the collision. Okay, I want you to look at these equations for a minute. This is conservation of momentum. This is conservation of energy. Let's suppose I know everything about what's going to happen or what's happening before the collision. So I know the masses of the two objects, I know V1 and I know V2. And I want to predict what U1 and U2 are going to be. Can I do it? How many unknowns are there in this equation, in these two equations?
2.
2, right? I don't know U1 and I don't know U2. How many equations do I have?
2.
2. 2 equations, 2 unknowns. Your 9th grade algebra teacher's voice should be ringing in your ears. If you have the same number of equations as unknowns, you can solve this thing, right? Now, if you remember, we did this for a simplified version where we said V2 was 0, right? And we did it in class on Wednesday, and it was like 2 pages of algebra.
Usual.
Okay, I'm back.
Welcome back.
Thank you. It's nice to be here. All right, let me get the screen sharing back up here. All right, there we go. And I want to do this thing. Okay, so 2 equations, 2 unknowns, right? Dang it, did I freeze again? Oh, come on. Okay, can you hear me?
Yes. We can hear you.
Okay.
You're just focused on the your webcam is on the paper.
Yeah, well, I'm trying to show you my screen. Are you guys seeing my screen?
There we go.
Yeah, we can see it now.
Okay. I don't know what the deal is with my internet this morning, but it's not playing nicely. So, okay, so we've got 2 equations, 2 unknowns, right? Your high school algebra teacher's voice should be ringing in your ears. 2 equations, 2 unknowns, you can solve it. Okay? But solving this version is even worse than the one we did last time. So, this is not an algebra class. How many of you have used Mathematica in the past? Or Wolfram Alpha?
I don't think I have.
All right, play with them sometime. There is software out there that will solve equations symbolically for you. If we're trying to teach you algebra, that's a bad tool to use because you won't learn algebra. You will just learn how to use the tool. But I'm not trying to teach you algebra. So if you run into some gross algebraic problem sometime and you don't want to try to solve it yourself, go plug it into Wolfram Alpha or Mathematica. Mathematica, I believe we have a campus site license for. So it's available on computers, at least in the physics department and the math department, and I believe in engineering as well. Okay? These things are your friends. Play with them sometime. Okay, I'm not going to show you how to do it, but if you do solve these things, this is what you get. Okay? You get these lovely equations that tell you what U1 and U2 have to be in terms of the masses and the velocities of the 2 objects, okay? Now, these equations are kind of gross, but let's look at them for a minute and see if we can make some sense. So, if I throw a bouncy ball at a huge rock, what happens?
It bounces off the rock.
Okay, what happens to the rock?
It just stays there.
Nothing, right? So in mathematical terms, that would mean if I make object 2 the rock and object 1 the bouncy ball, right? That means I would expect the velocity of object 2 to be 0, right? If I started off with the rock at rest, I would think I would end up with the rock at rest still, right? Okay, mathematically, do these equations do that? So I throw a bouncy ball with some really tiny mass and some big velocity at a rock with a huge mass and no velocity. I think what you just told me is that I should expect the rock not to move, right? So I should expect U2 to be 0. Well, let's see if that works. Okay, so U2 is equal to these 2 terms. One depends on the velocity of the bouncy ball. One depends on the velocity of the initial velocity of the bouncy ball. and the initial velocity of the rock. Well, the initial velocity of the rock was 0. So that means this whole equation over here, this whole term is 0, right? Because V2 is 0. So that goes away. Okay, let's look at this term over here, right? See if I can draw. So this term went away, right? That term's gone. This term is not gone. But we're saying that experience tells us it should give us 0. Why would that term give us 0 if this is a bouncy ball, M1 is a bouncy ball, and M2 is a huge rock?
We're assuming that M2 is big, right?
Yeah, M2 is really big, and M1 is really small.
So it's gonna go to 0 because when you divide, when you divide something small by something really big.
Exactly. Because this numerator is a small thing, right? It's the mass of the bouncy ball. So even if you double it, okay, you doubled the small thing, who cares, right? And then you add a small thing to a really big thing here in the denominator, which means that you divide a small thing by a really big thing, that's really close to 0, right? Okay, cool. So now let's look at this top equation. In our example with the bouncy ball and the huge rock, right? We said, okay, V2 is still 0, so this whole term is gone. Okay. Now let's look at this first term, this guy. Okay. M1 is really small, right? So M1 minus M2 is basically a small thing minus a really big thing. Well, that's pretty much the same as saying it's just the negative of the really big thing, right? And down here, I've got a really small thing plus a really big thing, which is the same as basically just saying it's the really big thing. So what I can basically do is I can say, okay, let's just get rid of this, and we've got negative M2 divided by positive M2, which is just negative 1, right? So what this is telling us is that the bouncy ball in a perfectly elastic collision should bounce off of the huge rock and go backwards at the same speed it went forwards into the rock. Okay? All right, so that's our ballpark view of how these things work, okay? So here's what we're gonna do. We're gonna come down here and we're gonna use these to look at how this set of balls dropping, right? So we had 3 balls dropping, how that works. So I'm going to come to there's a link in the presentation, or I've dropped the link in the chat that's going to take us over to a spreadsheet. Okay. I recommend, if you can, open up 2 windows. Have one looking at the spreadsheet, which I'm going to be sharing, and have one looking at the slide that we were just looking at. Okay. You can do it in whatever order. You can bring up both on your own computer, however you'd like to do it. But what I'm going to do is I'm going to stop sharing this, and I'm going to start sharing the spreadsheet. Okay. So first of all, why a spreadsheet? Why would I want to do this in a spreadsheet as opposed to just doing it by hand?
Because you can do like equations in the spreadsheet.
Yeah, I can do equations in the spreadsheet. If I'm punching this into a calculator by hand, what are the chances I'm going to hit a wrong number at some point?
Pretty high.
Yeah, I'd say like about like 700%, right? You're going to make on average like 7 or 8 errors over the course of this thing. Okay? So we're going to, so what we're going to do here is the first part we need to figure out is, okay, so what I've put in here is I've got these entries that show G, right, 9.8, the mass of the basketball. I've got a guess for the mass of the bouncy ball and the mass of the golf ball, okay, all in kilograms. What we need to do is figure out the height at which they were dropped from. And for the purposes of this class, I'm going to say they were dropped from a height of 1 meter. But we could put whatever we want in there. We could put 7 meters. We could put 25 centimeters, right? We could put whatever we want. But we're going to make it a height of 1 meter. Okay, so now the question is that basketball. How fast is the basketball going right before it hits the ground? And how would we figure it out?
We would calculate the acceleration due to gravity over 1 meter.
Yeah, we could do that. We could also do this using energy, right? And energy is really nice here because energy doesn't ask about how long it takes. We don't actually care how long it takes to fall, right? We only care how far it fell. So by using energy, right, and I'm just going to come over here and type it out. What energy does the basketball have or before it starts falling?
0.
Well, 0 kinetic. How much potential energy?
mgh.
Yep, m times g times h, right? So there's our initial energy. How about when it hits the ground? What kind of energy does it have there? Or right before it hits the ground?
That's all kinetic.
Now it's all kinetic. So now it has 1/2 times m times v squared, right? And if I solve that equation for velocity, what I get is that my velocity right before the ball hits the ground, right, the masses cancel out. I move the 1/2 over and I take the square root. It's the square root of 2 times g times h, right, to the 1/2 power, square rooted. Okay, so let's put that over in this cell. Because what that means is that all of the balls are going to be moving that fast right before their collisions. Okay? So I'm just going to type over here, I need the square root. Well, hey, look, it's got a square root function. So I want the square root of 2 times gravity times my height that they were dropped from. And I close the parentheses and I hit enter. And it says, okay, look, they were going that fast, right? Okay, so that's how fast they were going. Now let's think about when that ball hit the ground, the basketball hit the ground. If it's a perfectly elastic collision, this is exactly like the thing we just talked through, right? It's like the bouncy ball hitting a huge rock, except for this is a basketball hitting the whole planet, okay? So if it's a perfectly elastic collision, that means the basketball will be moving upwards with the same velocity it was moving downwards right before the collision, okay? So let's come down here and think about collision number 1. So in collision number 1, our basketball is going to be object number 1, and our bouncy ball is going to be object number 2. Okay, that blue bouncy ball they had in the middle. So V1 is going to be just that initial velocity, right? And it's going to be positive because the basketball is moving up right after the collision with the ground. Okay. How about the bouncy ball? What's V2 going to be? Let me ask it again. We want the velocity of the bouncy ball right before it hits the basketball. So how would we figure that out? Let's look at these equations. Are they any different if we do this for the bouncy ball than they were for the basketball?
No.
Why not? The masses are different, right?
Well, it's the same equation.
Yeah, it's the same equation, but the mass cancels out anyway, right? So as long as they dropped from the same height, which they did, right? Because they were all stacked on top of each other. As long as they drop from the same height, the velocity is going to be the same, just downwards, right? So it's just negative V naught. Okay, so there's our velocity of our basketball going up. Here's the velocity of our bouncy ball coming back down to meet it. Okay, so now I just have to fill in my masses. Well, the mass of the basketball I put right there. The mass of the bouncy ball I put right there. Okay, now I need to take those equations from the slide and put them in here. And it's a little bit messy, but bear with me, okay? If I say an equal sign, that tells it I want an equation, okay? And now I just need to do m1 minus m2 divided by m1 plus m2 times v1 plus 2 times m2 divided by m1 plus m2 times v2. Okay, I just typed in the equation, and every time I needed a variable, I clicked on the cell next to the variable I needed. And if I hit enter, I get a number. Okay, so this is the velocity of the basketball after the collision. You'll notice before the collision, the basketball was moving upwards at 4.4 meters per second. After the collision, we're predicting that the basketball is only going to be moving upwards at 0.14-ish meters per second. So almost not moving at all. Okay. And now I just have to do the same with U2, right? Okay, so U2 is 2 times M1 divided by M1 plus M2 times V1 plus M2 minus M1 divided by M1 plus M2 times V2. Okay, so interpret that number for me. What does that number mean for U2? What does it mean? We got a number out.
It means the velocity of the second ball after the collision, and it's more than twice the original velocity.
Right. So by just doing this, we've made it so that that bouncy ball is moving at twice as fast as it was right before the collision. Okay? All right. So now we have to think about the next collision, right? the bouncy ball running into the golf ball. Okay, so object number 1 is going to be our bouncy ball, and object number 2 is going to be our golf ball. So I know the velocity of the bouncy ball, right? I just figured it out. It's that number that I just calculated. Okay, how about the velocity of the golf ball? Well, we can come back over here, right? It's the exact same because they all fall together. It's just downward at this initial velocity. Okay, our mass 1 is just the mass of the bouncy ball. And our mass 2 is the mass of the golf ball. All right, now here's the great thing. I don't have to retype these equations. I don't have to, because I can copy them. Okay, Google Sheets or Microsoft Excel are smart. If you copy them, it will just move the references accordingly. So if I take these two and I copy and I paste, voila, if I look in here, it created the exact same equation. It just moved all the references down. So as long as I have the same ordering of cells, I don't have to retype anything. And we get that after the collision, the bouncy ball is going to be moving up at about 4 meters per second, and the golf ball is going to be moving upwards at 17.5 meters per second. Okay? Which is crazy, right? That is really fast for the golf ball. And this is how a supernova works. This is how you blow up a star. You don't blow up the middle of the star, but each successive layer steals energy and momentum from the layer below it, until eventually the layer right at the outer edge of the star has so much energy and momentum that it gets blown off into nowhere, right? It just goes flying forever. That's how you blow up a star. Okay, so practically speaking, there are a couple of things I want you to learn from this. I will not expect you to memorize these equations or be able to derive them on a test. I do expect you to understand where they come from and how you could get there, right? But here's the thing I want you to understand. I want you to understand how you can use momentum and energy in elastic collisions, right? Now, if I really did this with a basketball, a bouncy ball, and a golf ball, I wouldn't get the golf ball moving that high or that fast because I would lose a little bit of energy each time. But that's okay. I lose a little bit of energy each time. That's fine. Doesn't make not a problem. But if you think about what happens if you conserve kinetic energy, right? You don't lose energy each time. What that tells you is the maximum you could get out, right? So it gives you a limit that you know you won't go past. Okay, the other piece I want you to take away from this is that generally speaking, your calculator is not always the best tool for you doing numeric calculations, right? This spreadsheet did all of the math for us. It did not make any mistakes. How many of you guys watch The Office?
Well, yeah.
Okay, people will admit to watching The Office. Okay, there's this wonderful scene in The Office where Michael Scott makes his own paper company. And eventually he meets with an accountant, and his accountant tells him, you have no money. Your company is going to go out of business. And Michael Scott goes, can you recheck the numbers? And the guy starts going like, it's, you know, and Michael said, no, just recheck the numbers. And so he goes, crunch, and just hits enter again, right? Because the spreadsheet program doesn't make mistakes. It doesn't misadd numbers, right? There is no rechecking the numbers because these are the numbers. The spreadsheet did the math correctly, right? So using tools like a spreadsheet or some of the more complicated tools you can use helps you out because you will not make arithmetic errors in a spreadsheet. Now, that doesn't mean you won't make mistakes, right? If you look at these formula, they're long enough that it's very easy to make a mistake, to miss a multiplication sign, to miss a division sign, to do an addition where you should have done a subtraction, right? But you won't make a mistake in punching the wrong number in. And the calculations are instantly reproducible. So for example, let's say I wanted to run the same problem, but I wanted to make the bouncy ball heavier, right? I'm going to make it 300 grams instead of 200. I hit enter, and voila, everything automatically updates, right? Instead of getting 17.5 meters per second for the velocity of the bouncy ball or the golf ball, I get 16.4. Okay. What if I made it 100 grams? Well, I rerun the numbers and I get something else, right? What if I made it 250 grams, right? And I could play around with this thing. I could play around to my heart's content. Okay. Okay, how are we feeling? So this is a type of skill that I hope is useful to you. I will not put this on a test. I can't make you do spreadsheets on a test. I don't know how to do that. But I can show you how to use it and hope that it's helpful for you. And now you could do this for homework problems. You can do this for all kinds of things. Okay. Questions, comments, concerns? All right. So when somebody asks you, what you did in class today, you can say we learned how to blow up stars, and you're actually right. That's exactly what you did today. Okay. I'm going to go ahead and stop the recording then. And let's see, I'll stop sharing that, and we'll go ahead and shut down our recording. And I'll stick around for homework questions or lab questions or whatever questions. But if I don't, have a nice weekend, and I'll see you Monday.
Take care, Dr. Nelson. See you in seminar.